Welcome to a journey into the future of computing, where the next revolution isn't happening on circuit boards, but in petri dishes. While our digital world runs on billions of energy-hungry silicon transistors, scientists at Imperial College London have made a breakthrough that could fundamentally transform how we think about computation. They've successfully engineered E. coli bacteria to function as biological computers, using minimal energy while performing complex calculations. Join us as we explore this groundbreaking technology that harnesses billions of years of natural evolution to create computers that think through biological processes. Our modern world relies on massive server farms filled with silicon-based computers that consume megawatts of electricity and generate substantial heat. These traditional computing systems currently use about 2% of global electricity, with projections suggesting this could increase to 8% by 2030 due to artificial intelligence and increased digitalization. This growing energy demand poses significant challenges for our global climate goals and sustainable future. As we push the boundaries of conventional computing, we're facing fundamental limits in efficiency and environmental impact that call for radically new approaches. In a groundbreaking study published in Nature Biotechnology, Dr. Meera Krishnamurthy and her team at Imperial College London have successfully engineered E. coli bacteria to function as biological logic gates, the fundamental building blocks of computational systems. Unlike silicon transistors, these bacterial circuits use proteins and genetic material to process information. The team developed what they call transcription factor-based logic modules that can be assembled into functional circuits within living cells. These bacterial computers respond to specific chemical inputs by producing corresponding protein outputs, effectively mimicking the binary operations of electronic computers but through biological processes that evolved over billions of years. What makes bacterial computing truly revolutionary is its incredible energy efficiency. According to Dr. Krishnamurthy, these bacterial logic gates consume approximately 1/10,000th the energy of their silicon counterparts. A single gram of these engineered bacteria could theoretically perform calculations that would require several watts of power in conventional computing systems. This efficiency isn't surprising when you consider that nature has been refining these biological computational processes since life began. The bacteria operate at room temperature and can be powered by simple sugars or even waste products, eliminating the need for external power sources or complex cooling systems. While bacterial computing has been theoretically possible for years, the recent breakthrough centers on scalability and standardization. The Imperial College team developed a modular system where different bacterial strains can be combined in predictable ways, similar to how electronic components are assembled on circuit boards. This standardization is crucial for moving bacterial computing from scientific curiosity to practical technology. Researchers can now design bacterial circuits with specific functions and combine them to create increasingly complex computational systems, opening the door to real-world applications that were previously impossible. One of the most promising immediate applications for bacterial computing is environmental monitoring. In March 2023, the research team demonstrated a proof-of-concept bacterial computer that could detect multiple water contaminants simultaneously and produce an easy-to-read output signal, all without requiring external power sources or sophisticated equipment. This makes the technology particularly valuable for remote regions or developing nations with limited electricity and technical infrastructure. Imagine distributed networks of bacterial sensors monitoring water quality, soil conditions, or air pollution in areas where traditional electronic sensors would be impractical or too expensive to deploy. The medical potential of bacterial computing extends far beyond simple diagnostics. Biotechnology startup Cellular Logic, which spun off from Imperial College Research, recently secured $17.8 million in funding to develop bacterial computers for pharmaceutical manufacturing processes. These living computers would continuously monitor and adjust chemical reactions in bioreactors, potentially reducing the production costs of certain medications by up to 40%. This could make essential medicines more affordable and accessible worldwide. The bacteria are simultaneously acting as sensors, computers processing the data, and actuators implementing required changes, an all-in-one biological solution that could revolutionize how we produce pharmaceuticals. Dr. James Chen, Chief Technology Officer at Cellular Logic, envisions broader applications. We're developing bacterial systems that can operate inside wastewater treatment facilities, continuously analyzing contaminant levels and adjusting bacterial populations to optimize purification processes. These intelligent bacterial systems could dramatically improve the efficiency of water treatment, reducing energy consumption and chemical usage while improving water quality. Unlike traditional automated systems that require extensive electronic infrastructure, bacterial computers can operate directly within the treatment environment, responding in real time to changing conditions. The sustainability benefits of bacterial computing extend far beyond energy consumption. Unlike electronic waste, which contains toxic materials and is notoriously difficult to recycle, decommissioned bacterial computers can be simply composted. This cradle-to-cradle approach represents a fundamental reimagining of technology's relationship with the natural world. Preliminary life cycle assessments suggest that bacterial computing could reduce the carbon footprint of specific computational tasks by over 99% compared to conventional methods. Dr. Nandita Sharma, an environmental technology researcher, notes, "We're witnessing the emergence of truly sustainable computing. While these bacterial systems won't replace your smartphone anytime soon, they could handle specialized computational tasks in remote or resource-limited settings with minimal environmental impact." Despite the promise, significant hurdles remain in bacterial computing. Current bacterial systems operate much slower than electronic systems, with computation times measured in minutes rather than nanoseconds. They also face challenges related to long-term stability, as mutations can potentially alter their computational functions over generations. Researchers are exploring various approaches to address these issues, including genetic safeguards that prevent drift in computational function. The technology must also overcome challenges related to standardization, reliability, and integration with existing systems before it can be widely adopted for critical applications. The technology also raises novel biosecurity questions that traditional computing never had to address. In April 2023, the International Bioethics Commission released preliminary guidelines for programmable biological systems, emphasizing containment protocols and built-in genetic safeguards. These include engineered dependencies on laboratory-supplied nutrients and genetic kill switches that render the bacteria non-viable outside controlled environments. Regulatory frameworks are still evolving, with the European Union recently establishing the Advanced Biological Computing Advisory Group to develop standards specifically for computational biological systems, distinguishing them from traditional GMOs and electronic devices. This regulatory uncertainty represents one of the most significant barriers to commercialization. Many experts envision not a wholesale replacement of silicon computing but rather a hybrid approach where biological and electronic systems work in tandem. Electronic systems would continue to handle high-speed, general-purpose computing, while bacterial systems would perform specialized tasks like environmental sensing, biomedical monitoring, and sustainable materials production. Last week, researchers at MIT announced a new technique for interfacing bacterial computers with electronic systems, potentially allowing for seamless communication between biological and silicon-based computation. This hybrid approach could combine the best aspects of both computing paradigms: the speed and reliability of electronics with the efficiency and sustainability of biological systems. The field is advancing rapidly with innovations that push the boundaries of what's possible. A research consortium in Singapore has demonstrated bacterial computation using engineered cyanobacteria that derive energy directly from sunlight, eliminating even the need for sugar as an energy source. These photosynthetic computing systems represent the ultimate in sustainable technology: computers powered directly by the sun through biological processes. This development could enable completely self-sufficient computing systems that could be deployed in remote locations without any need for external energy inputs, truly merging computation with natural processes in a harmonious way. At this technological crossroads, bacterial computing reminds us that nature has been processing information since the first cell divided billions of years ago. Dr. Krishnamurti notes, "We're not just creating new technology, we're establishing an entirely new technological paradigm that blurs the line between computation and life itself." That comes with profound responsibilities. Perhaps the future of computing isn't just about building faster chips, but about reimagining computation itself through the lens of biology, harnessing the computational power inherent in life to create technologies that work with nature rather than against it. This perspective shift could fundamentally change our relationship with technology and the natural world. As we've explored throughout this journey, bacterial computing represents far more than just another technological innovation. It's a fundamental reimagining of what computation can be. By harnessing the information processing capabilities that nature has refined over billions of years, scientists have created computing systems that consume a fraction of the energy of traditional electronics, can be powered by simple sugars or even sunlight, and return harmlessly to the Earth at the end of their life cycle. While bacterial computers won't replace our smartphones or laptops anytime soon, they open up entirely new possibilities for sustainable environmental monitoring, medical diagnostics, pharmaceutical production, and wastewater treatment, particularly in remote or resource-limited settings. As this technology continues to evolve, overcoming challenges of speed, stability, and regulation, we may be witnessing the emergence of a hybrid computational future where biological and electronic systems complement each other's strengths. Perhaps most profoundly, bacterial computing invites us to reconsider our relationship with technology itself, not as something separate from the natural world, but as an extension of the computational processes that have been occurring in living organisms since life began. In this vision of the future, our most advanced technologies may be those that work in harmony with nature rather than in opposition to it. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.